code. Let's start. So the task is cathode ray tube. You avoid the ropes, plunge into the river and swim to shore. The elves yell something about meeting back up with the upriver, but the river is too loud to tell exactly what they are saying. They finish crossing the bridge and disappear from view. Situations like this must be why the elves prioritized getting the communication system on your handheld device working. You pull it out of your pack, but the amount of water slowly draining from the big crack in the screen tells you it probably won't be of much immediate use. Unless, that is, you can design a replacement for the device video system. It seems to be some kind of cathode ray tube screen and simple CPU that the boss driven by precise clock circuit. The clock circuit ticks at constant rate. Each tick is called a cycle. Start by figuring out the signal being sent by the CPU. The CPU has a single register X which starts with the value 1. It supports only 2 instructions. Add XV takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V can be negative. Nope, take 1 cycle to complete. It has no other effect. The CPU uses this instruction in the program your puzzle input to somehow tell the screen what to draw. Consider the following small programs. Nope. Okay, we do nothing. Execution of the program proceeds as follows. At the start of the first screen, the nope instruction begins execution. During the first cycle, X is 1. After the first cycle, the nope instruction finishes execution doing nothing. At the start of the second cycle, the add X instruction begins execution. During the second cycle, X is still 1. During the third cycle, X is still 1. After the third cycle, the add X instruction finishes execution, setting X to 4. Okay. At the start of the fourth cycle, the add -5 begins execution. During the fourth cycle, it's still 4. During the fifth cycle, it's still 4. After the fifth cycle, the add -5 instruction finishes execution, setting X to -1. Maybe you can learn something by looking at the value of the X register through the execution. For now, consider the signal strength, the cycle number multiplied by the value of X register during the 10th cycle and every 40 cycle after that. That is, during the 20th, 16th, 100th, 140th, 118th, and 220 cycles. For example, consider this large program. So I see. And the interesting signal strength can be determined as follows. During 10 cycles, the register X has the value 21. So the signal strength is, okay, we need to multiply it and then get it. And then we need to multiply signals on this period of time. The sum of the signal strengths is like that. Okay, find the signal strength during this time. What is the sum of these 6 signal strings? Okay, let's parse our input. Quite large input. Let's parse our input, then run it. Yeah, and then we need to parse it again. Let's do split into parts like that. So strings, split line, white space, and then we need get the command 0, and then switch cmd if and also need some counter of cycles. We know that we need to calculate on this cycle, so that we know that our cycle store our CPUs, let's call it CPU, CPU array should be, I don't know, 22 integers. So case Nope, you do nothing. Also we need some counter. Do nothing, just increase it. Then if it's case edX, then we know that like the first value at 0 cycle is 1. Yeah, so x equals 1. Then and the value will be the same. So after nope, the value is the same. So CPU I assigned to x, and for so we know that it's still x, but after 1 cycle start of second cycle instruction begins execution. During the second cycle x still 1. So yeah, we need to calculate x, and then if we know that it's need to get arc. Toy 2 parts 1 and arc plus like that. So yeah, let's print let's print CPU. So for the simple example, it would be 1 minus 4. So at the start of the first cycle, the loop instruction begins execution. During the first cycle x is 1. At the start of the second cycle, okay, so at the start, so plus, we do I plus plus, and then assign x, and then we do again I plus plus, and then assign x arc, let's start from the 1. Yes, so at the start of the first cycle, the loop instruction begins execution. During the first cycle, x is 1. First cycle x is 1. After the first cycle, the loop instruction finishes execution, doing nothing. At the start of the second cycle, at x3 instruction begins execution. Okay. So after second, it begins execution. During the second cycle, x till 1. During the third cycle, x till 1. But after the second cycle, the add x instruction finish execution setting x to 4. Okay, at the start of the fourth cycle, the x instruction begins execution. During the fourth cycle, x still is 4. So let me think. So during why here is again 1. Yes, so here we know that stays the same. During the fifth cycle, 1, 2, 3, 4, 5, still 4. After the fifth cycle, the add x instruction finish execution. Okay. To -1. The add x instruction finish execution set x to -1. Yeah, we don't need x. Because we initialize CPU 0 as 1. So after fifth, 1, 2, 3, 4, 5, it equals -1. Okay, so let's check in the other problem, other input. Okay, let's create more than interesting. It's a lot actually. Okay, so let's see the let's see the values at 20, 6, 20, 60 and 100. Yeah, so fmt println 20, 60, 100, 140, 180, and 22. So CPU 20, CPU 60, CPU 100, CPU 140, CPU 180, and CPU 20. Let's run it. Now also we need to look printf. Yes, so 20, 21, 20, the 60 is 90, okay, 21, 60 is 90, 100 is 80, 21, 16, yes, it looks like, and the last one is 19 for some reason, but it's 80. Strange. Let's format it. Yeah, for some reason it's 90. It's not. It's not 80. Let's see. So 90. So maybe we check not at the beginning, but like at the end, but still on this second it equals. So at the beginning of the second, not at the end. Yeah, let's create three-dimensional array. Two-dimensional array. So at the beginning and at the end it's 1, but when it's no, it's the same at the beginning and at the end. But if it's arc, so again at the beginning, but here it's at the beginning, it previous one. Yeah, but at the end it is plus. So, and we need to check the values at the beginning. 0, 16, 100, 0, and 0. Okay, let's check. Oh my god. Something completely went wrong. So it looks like the start is always 1. So on previous one, so here it starts and the ends. And it's always the previous one, and the previous one I think also like that. Yeah, 17, So let's draw. So we have start on each second. We have start and finish. Then it's start and finish, and also it's start and finish. And if we want to add, we draw the same, finish the same, but then at the end it was previous, but start the same. And if it ends, if it's different, we need to get the last one. So nope, I think we need to check if they equals. Yeah. And for edX we also we get for next we get for X we get it, and for 1 we also get the last. Yeah, 29, 90, 80, 80, 30, 60, 80. Yeah, for some reason for 140 it's 30, 130, but it should be 21. So I think here we also need to copy it. Yeah, 21, 60. Yeah, so we copy the last one, like a noop. Actually, we get the same noop operation. And if we multiply it, like signal equals 1 as a sum, so it should start with 0. Yeah, let's count it, signal. Actually, we can we don't need to allocate all the array. I think we can just go and support current, just previous one and next one, but we already do that, so maybe it's okay. But yeah, actually we need previous one and the next one, and that's it. But let's multiply it. So let's do the mass. Multiply 20. Signal. It's plus, then signal plus CPU 60. Then 100, then 140, then 180, and then 220, and print our signal. Okay, so maybe you can do that in, like, we don't need actually to store it. Maybe we need just previous and next one. Yeah, 13 thousandths and 140. Okay, So let's check on our example. Let's check it. Yes, it's already an example, so we need larger input. It's not so large. Looks the same, actually. Okay, 40,360. Let's check. Yes. Okay. So let's do the second part. It seems like the X register controls the horizontal position of sprite. Specifically, the sprite is 3 pixels wide, and X register set the horizontal position of the middle of that sprite. In this system, there is no such thing as vertical position. If the sprite is horizontal position, put a pixel where the CRT is currently drawing, then those pixels will be drawn. You count the pixels on the CRT, 40 wide and 6 high. So the CRT screen draws the top row of pixels. Then the row below that, and so on. The leftmost pixel in each row is the position 0, and the rightmost pixel at each row is position 39. Okay, we have exactly like cycle during 40, cycle 1, cycle 40. Like the CPU, the CRT is tied closely to the clock circuit. The CRT draws a single pixel during each cycle, representing each pixel of the screen as okay. Here are the cycles during which the first and last pixel in each row are drawn. First pixel and last pixel are drawn. By carefully timing the CPU instruction and CRT drawing operation, you should be able to determine whether the sprite is visible in the instant each pixel is drawn. Is visible the instant pixel is drawn. If the sprite is positioned such that one of its 3 pixels currently being drawn, the screen produces a lit pixel. Otherwise, the screen leaves the pixel dark. Okay, it's either dot or number. The first 3 pixels from the larger example above are drawn as follows: sprite position 3, start cycle 1, begin executing at X. During cycle, CRT draws pixel in position 0, current CRT row. Okay, oh my god, quite big problem. So begin executing at X, CRT drawn pixel at position 0, current CRT row, like that. During cycle 2, CRT drawn pixel at position 1, current CRT 2, and to the cycle 2 finish executing at X. Register X is now 16, sprite position, like that. So begin executing at X minus 11. During cycle 3, CRT draws pixel at position 2. Okay. During cycle 4, CRT draws pixel at position 3. End of cycle 4. Finish executing at the ratio X is 5. Okay. Again, begin executing at X. During cycle 30, drawn pixel at position 4. Current CRT row. During cycle 6, CRT drawn pixel at position 5. End of cycle 6, finish executing X at 6, register X is now 11. Sprite position. Allowing the program to run to completion causes CRT to produce the following image. Render the image given by a program. What 8 capital letters appear in your CRT. What? 8 capital letters? Oh my god. Okay, let's check. So we need to, on picture we have sprite, sprite positions. But where are them? Okay. Seems like X register controls the horizontal position of sprite. What is sprite? The sprite is two-dimensional bitmap. Okay. Specifically, sprite is 3 pixel wide, and X reset the horizontal position of the middle of the sprite. Okay, we have 3 bits, 3 pixels wide, and X is a central sprite. In this system, there is no such thing as vertical position. If the sprite is horizontal position, puts a pixel where CRT is currently drawing, then those pixels will be drawn. CRT, который YouTube. So if pixel, if we set a pixel, it will be drawn. You count the pixel on CRT 48 and 6 high. Okay. The CRT screen draws the top row of the pixel left to right. Then the row below that, and so on. The leftmost pixel in the row is in position 0, and the last in position 39. Okay. Like the CPU, the CRT is tied closely to the clock socket. The CRT draws a single pixel during each cycle. Okay, representing each pixel on the screen as number. Here are the cycles during which the first and the last pixel in each row are drawn. Here are the cycles during which the first and the last pixel in each row are drawn. Okay, so by carefully timing the CPU instruction and the CRT drawing operations, you should be able to determine whether a sprite is visible or in the instant each pixel is drawn. Is visible the instant each pixel is drawn. If sprite is positioned such that one of 3 pixel is the pixel currently being drawn, the screen produces lit. Otherwise, the screen leaves the pixel dark. The first few pixels from the large example above are drawn as follows. So, sprite position. The first few pixels from the largest example. So I have 3 pixels. Begin executing during cycle 1. During cycle 1, CRT draws pixel in position 0. Current CRT row. During cycle 2, CRT draws pixel in position 1. Okay, current CRT row 2. End of cycle 2, finish executing at X, reach the X is now 16. Sprite position. So it's 3, 3, 3, 3, 3. So when in sprite position we just move it. Start cycle 3. Begin executing at x minus 1, minus 11. Set the rows pixel position 2. CRT draw pixel in position 3. Y. Minus 11 registered x is now 5. Minus 11. Begin executing at x6. CRT draws pixel in position 4. Then I started wrong for position 5.